Okay, so this morning I will talk about the following. We looked at the people that were attending this seminar, and some people were relatively new to this, so I will spend about 2 minutes about explaining about triples and graph databases. Then I'll spend another minute talking about AllegroGraph features. I really promise I'll keep that short. Then I will look at how AllegroGraph in the past was doing a loading, indexing, and querying. And I can already tell you that we were doing really well on loading and indexing, but we were slow when we were querying on reasoning triple stores. And I'll explain why that was. Then, as Steve just mentioned, we've been working hard on a query optimizer this winter, and I will give you some statistics for how we're now doing, where we compare 3.1 versus 3.2, and we'll compare AllegroGraph versus some other triple stores that start with an O and that do reasoning too. And then finally, I'll show you a little bit how we do things internally when we take SPARQL or Prolog queries and make them fast. I have to apologize the people that usually listen to my talks. Is usually I try to have not too much code recently, but this time there will be a little bit more code again. Our director of sales always tries me not to do it, but he's having a baby right now, so I have my chance to go a little bit deeper into code. But let's start with graphs, triples, and the triple store. So for those who've never worked with a triple store, if you look at the relational database, you usually start with making a schema, and then you fill in the data in your schema. With the triple store, basically what you do is you say create triple store. This is how we do stuff in one of our Python APIs. You create a triple store, now you have a triple store, and then without making a schema, you can start adding triples. And you could say that there's a person, Steve, who's an organizer in 52, or Jans is a psychologist in 50, Craig is a person at 32. Oh, this is still very regular. Why not do this in a relational database? Well, the first big difference is that in a triple store you can add one-to-many relationships incredibly easy. No indirect link tables, you can just add it, and because this is the semantic web, you can say whatever you want to say. So I can say that person likes pizza. And then you have a graph. Because what you see here, you see the link, the nodes, and you see the link between the nodes. And then without adding any schemas, you can just keep adding information. So, by the way, this is our thick client called Graph, which is our AllegroGraph browser. And keep adding information. I can say that person 3 is a neighbor of person 1, and person 3 is a neighbor of person 2. And suddenly my graph got a little bit more complex. I now see more relationships here in the middle. And here you see the neighbor of relationship. And once you've done that, you can query your database, and we provide 2 ways to do it. One is SPARQL and the other is Prolog. SPARQL is the W3 standard for querying databases, but it's like SQL. It's an access language, whereas our Prolog is the thing that you see here. Looks for simple queries nearly the same. It's more like a full language where you can make rules and do slightly more complicated things than you could do in SPARQL. And then with the triple store, you can do reasoning too. So I could add a triple that said first name domain person. In English, that means every subject that has a predicate first name must be of type person. If I add that triple, then suddenly we see that person 1 and person 2 and person 3, who all have a first name, are now suddenly a person. So this is probably the shortest way ever to explain what reasoning is in a triple store. So that about the triple store. We have on top of that a thick client on Windows and on Linux, unfortunately not on the Macintosh, where you can do SPARQL queries, and then here you get your results. I can click on something and suddenly I get the full graph for the results of my query. And so this is the graph view of the results of a query. And if I wanted to look at this thing, I could click on that and I would see more details of a particular node in the database. So this is more like a traditional database view. And then in 3.2 we will also release a new web browser for our triple store. It's called the AllegroGraph Web View Browser, and I give a small quick demo of that. Oops, let me go there. So this is the AllegroGraph Web View. I can do queries. I can choose here between SPARQL and Prolog. I'm doing this. So what we see here is I have a triple store open. Actually, I have a few triple stores open. Here's one, which is the Lubum 8000. I'll talk about that one in a little while. It's a triple store that has 1.1 billion triples. In this database, the reasoning is enabled. Here's some namespaces that I've added before. And then I can go to the recent queries, and I can say take this SPARQL query, and it already executed it. So this is, let me do this for a new query, otherwise you won't believe me. So I will say new, and so one of the cool things, by the way, about this web browser is that it does parenthesis matching. And so what you see here is it will match the, it will match and it will do the indentation right. And I can execute it, and here I get the results, and I could click on any result, and then we'll see that there is a graduate student 44, there's an email address, there's a member of something. This is artificial data, by the way, from the Lubum benchmark. And I can do the same queries in Prolog, so this is actually the same query in Prolog, and you see the same result here, and then again I can click on that and I get into this data in this view. Okay, so this is about a triple store. Let me go back to the presentation. Some features of AllegroGraph. We are a very scalable and of course a persistent triple store. We load 1.1 billion triples in 20 hours on a single CPU machine and 8 hours on a 4-processor AMD machine. If we do that, then we do actually load the data in 4 streams in federation. Federation basically means in our system that you can have a collection of triple stores on the same machine, on our different machines. Then you create a federated database, which basically is a set of pointers that point to other databases. And then our Prolog and SPARQL and Reasoner will work against this abstract store, and the query engine will figure out where your triples are. We are compliant with all the standards, so we don't lock you in. So we do RDF, RDFS, OWL, and SPARQL, and all the other things here. We have one proprietary thing, which is this RDFS++ Reasoner, which is not a full OWL Reasoner, but a subset. So we do everything in RDFS, and then OWL things like inverse of same as has value, transitive property. It might be proprietary, but both Oracle and OWLIM are basically having the same reasoners. And I guess that in the near future there will be some kind of standard for the slightly more restricted OWL reasoning. And then we do full text indexing, and we have Java and Python interfaces to the triple store. And in addition, we do some things that no other triple stores do. We native data types like numbers and dates are part of our entire indexing scheme. So we are just as efficient as relational databases in doing range queries. And given that we have that feature, we also have created libraries for spatial reasoning, for temporal reasoning, and we have full social network analysis on top of our triple store. But all this stuff is handled in all the seminars that I gave before. So now let's go to the main bulk of my talk, which is about optimizing our query engine. So, as I said before, AllegroGraph always has been really, really fast in loading and indexing, but we were losing against the competition when we had to reason over really large triple stores. And the reason was that triple stores that do reasoning always use this trick called materialization. So what you do is you load your data, you index your data, then you start the reasoner and you do all the inferences that you can think of. So you do type inferences and maybe some normalization of predicates. And then once you've done that, you have 2 or 3 times as many triples. You index that again, and then you do your queries, which will be fast. We didn't do it because most of our customers actually wanted a dynamic triple store where you could keep adding triples and then instantly do your queries. But so we were kind of slow on those queries because of that. But for us, of course, it was not a really good position to be in. So we worked hard this winter, and now we have still a dynamic store where you can keep adding triples and you don't have to do any materialization, and the queries will be fast anyway. Well, let me show you. So we did our optimization work on the 3 different types of data sets. The Science Commons with life science data, the linked data that most people are familiar with, and I'll go into that, and then Lubum 8000. But let's look at these data sets. So one of them is from the Science Commons. It's an effort by the Science Commons community to create kind of a portal for many different life science databases, gene databases. There's a thing in here that's got the very detailed analysis of the brain. There's the PubMed, all the publications in this field, and we're able to do queries that look at all these databases at the same time. Then most people in the semantic web have seen this picture where you take all kinds of public available data sets, put them in SPARQL endpoints, and then do interesting queries against them. About half a year ago, one of my colleagues, Gary King, gave a talk, which is also on our website, where we showed how we can do queries where we use the DBpedia, which is kind of the IDF version of the Wikipedia, GeoNames, which is a database of about 6 million places on Earth, and the US Census data, and we could do queries where we say find the socioeconomic indicators for the place where Obama was born, where you both need to find where Obama was born in the DBpedia, where you want to know about the place and GeoNames, and then you want to know about the socioeconomic indicators in the US Census database. And then finally, we work with the Lubum 8000 database because that is the de facto standard for reasoning triple stores. I gave you here the web address. You can go there. And what it is, it's an ontology of what a university is. And then there's a generator where you can make your data sets as large as you want, where you create a number of universities and departments within the universities. Here's a little part of the class hierarchy of Lubum. This is only part of it. For example, here you see the class diagram for an employee and the subclass relationships and the types of professors that you have and the director and things like departments and organizations, stuff about students. And then there's all kinds of predicates defined in the system and domain, range, and inverse and subproperty of relationships. So it's a big data set with an ontology where you have to do all kinds of inferences. You don't need much of OWL, but with our RDFS++ reasoning, you can do all the reasoning that they had in their 14 benchmark queries. So what I'm going to show you is how we do on the Lubum benchmark, on the 14 queries in the Lubum benchmark. And we'll use Lubum 50, which is about 7 million triples, and Lubum 8000, which is 1.1 billion triples. We do the experiment on a 4-processor 1.8 gigahertz 16 gig machine, and what I'll show you is both a comparison of 3.1 against 3.2 and one other vendor against 3.2. So first let's look at the comparison between our current AllegroGraph and the one that will come out within a few days. So what you see here is, if you look at the total query time for all our 14 queries, was taking more than 250 seconds, and now we're done in just 2-3 seconds. So it's almost 100 times as fast. And that's not entirely honest, because most of that performance came in query 9. That was really, really slow. So let's just forget about query 9 and how slow that was in 3.1. And let's look at the queries without query 9. And what you'll see is that 3.2 became faster on nearly every query except query 14. So it's still 10-fold speed up for the queries that are in the range of 1 to 6 seconds. Now we can also look at the queries in the range of 0 to 0.1 seconds, and then again we see that on most queries, at least on the bigger ones, we got substantially faster. So now the question is, does this also work for really huge triple stores where you have a billion triples? And what we do here is we compare AllegroGraph 3.2 against another triple store. I can say it's AlLim. And what you see is that the total query time for AllegroGraph 3.2 is faster. Well, what does this consist of, this performance gain? Well, again, we see that in query 9 we get a really big improvement with respect to the other database. And for the intermediate ones, we're roughly the same. So let's get rid of query. Oh, let's look at the small ones, and you see that even for the very small ones, AllegroGraph is now blue. We're kind of faster for all the queries. So we now get into the same range as the triple stores that do materialize, and for us that's a big deal, because as I said before, most of our customers want dynamic triple stores where you can keep on adding data and you get good performance. If you look in general at all the triple stores, just to give you a statistic, is usually what you see is you load your data, and it takes some time. So if you load a billion triples, for other triple stores, a single CPU, it might take more than a day. But then you also would have to wait hours and hours and hours before you do your full type materialization. And then query time is almost nothing compared to load times. So here we give you the data for another database, for AllegroGraph on the single CPU, and AllegroGraph on federated. So with 3.2 we're much more dynamic. You can add a few triples, delete or change the whole ontology, and then you're back into doing queries within a few minutes. So it still does take a few minutes because we build up some dynamic indices now on the fly, and you can decide after loading the triples to rebuild all these new indices at one time, or you cannot do it, and then when you do the queries, these new indices will be built on the fly. And you get a little bit of a performance hit if you hit some particular new predicate for the first time. So how do we do this? Or maybe I should stop here and take some questions.
Well, there was a question earlier on when you were talking about federation. It says, so this is a distributed system. I answered yes, but I don't know if there's any more to...
Yeah, this is a distributed system in the sense that you can... So what we see is that if you create triple stores on the same machine, then you get a little bit of a performance hit, but just a few percent. If your triple stores are on a SAN, then again, you keep really good performance. If your triple stores are on a really distributed machine, then query time will go down a little bit because you have now to go for sockets and much more communication between stores. But yeah, in essence, the programming model for someone doing a query doesn't matter where the triples are. It will be completely distributed. So how do we do this? So now a little bit of code. So the query optimizer that we built was initially built on top of Prolog, and that was because our reasoner the RDFS++ reasoner was built in Prolog, so we did all the optimizations there. But we can take the SPARQL query, something like this. This is query 9, which is always taking a long time. We take Z is a type of department where Z is a sub-organization of Y. This involves transitive reasoning because a sub-organization is a transitive relationship. And then a person has an undergraduate degree from a Y, where X is a member of, let me see, Z. Member of C is one of these inverse queries, and then some type reasoning. So this is a query that does a lot of reasoning. And we take the SPARQL, we parse it into Lisp. Now it looks like this, and then it's just a little step to rewrite this in Prolog. And then we give you this. Well, this is the Prolog, and then this is the thing that we're going to optimize. So we use a statistics-based query planner, where we also do some tricks to make reasoning more simple. And so we would take the query and create it as something like this, and let's make it a little bit easier to read. So we basically rewrite the Prolog query that you saw before into this thing, and this thing is then finally executed. So it's hard to recognize now from the original query what it looked like. Basically, we created these internal maps that will be around for most of the time. And then this is still a call directly to the database. And then here we look in the indices again. Here we do a little bit of reasoning to find about types. And of course, when we say that this is internally executed, what we really mean is that this is compiled to Lisp, which is compiled to machine language. So actually what we do ultimately is we go all the way down from SPARQL to machine language for fast query execution time. And this is about the whole translation process to get to fast queries. Now we're almost there. So as we said before, 3.2 is here in a few days. You can call us if you want to pre-release now. All the queries, the query optimizer is fully working for Prolog, and we are in the process of taking SPARQL and translate it into Prolog. So 3.2 will not contain the completely optimized SPARQL yet. We are the problem is that if you look at the Lubum queries, they're all very, very easy to do because they almost look syntactically the same as Prolog. But if you start working with SPARQL queries with complex filters and all kinds of unions and optionals and all these things, then it takes a little bit more time. So we're now looking in how we can take, say, 80% of all the normal SPARQL queries and just do a straight translation to Prolog, and then we have to do a little bit more research to take the complex edge cases in SPARQL to turn it into Prolog too. And I would say that's all. Thanks very much. So any questions?
There was a follow-on to the federation. Why is the federation faster?
Well, federation is faster for loading because you can use multiple processes to do your parsing of your triple files and the sorting and the indexing. And the more processes you have, the faster that will go. However, if you have only one disk, then federation won't make your loading much faster. It's better if you have one machine but multiple disks, because then your I/O wait time goes down. And then queries also won't be faster with the federated store. Queries will be faster if you have just one single store, because in the other case you have to look in multiple triple stores. And so you get a small percentage of a hit in some cases when you do queries over a federated store.
There's a question about the Prolog. Are we using a special version of Prolog like SW Prolog for the reasoning?
Is it SWI or SW Prolog?
It's asking about SW Prolog, but really just asking about our version.
Our triple store is written in Lisp, and in our Lisp contains a full Prolog compiler, and it's a fast Prolog compiler. If you look at what was the name? Lips? I think it's Lips, the benchmarking stuff. And we're several times faster than SWI Prolog from Amsterdam. And we're roughly the same if you compare to the commercial Prologs, of which there are not many around anymore. Oh, one question is, I assume the query optimization is done automatically for you. Yeah, that's completely automatic. And by the way, you can add to your query that you want to, for example, only see the query plan. So you can do a query and then say query plan only, and it will show you in what order the clauses are executed and which internal indices are built on the fly. Okay, one question is, what level in the client to storage stack is federation implemented? I asked because I'm building application in Ruby but only find federation examples in Java and Lisp. I can help you there. What we can do is we have a Python client now that works using our REST interface, and it's a open source implementation of that Python client library. So what you do in the client is you define a federation, but the federation is done on in the server. So you can just define in the client over which set of databases you want to do your federation, and then it's done automatically for you. Send an email to Steve Sears, and he'll send you the sources for the Python implementation of the client, and then you can see how we do it there. Actually, if you're interested in doing work with Ruby for the REST interface, you should give us a call anyway.
So here's a question, and we're using comparing the numbers with Big OWL-AM or Swift OWL-AM. And this was the numbers that are published on the OWL-AM website for Big OWL-AM.
Yeah, but as I said before, I am not so much interested in whether they are a little bit faster than we are or they are faster. I mean, I want to be in the same area, because what we find important is that we can stay dynamic, that you can add an ontology, take out an ontology, update an ontology, add some data, and keep on doing your queries instead of waiting half a day or a day for materialization.
Okay, there's a lot more coming in, so I'm going to try to get to everybody.
So you mentioned that the optimizer, so that's a question from Robert. You mentioned that the optimizer is based on statistic. Is the statistics of the data, or does it also account the statistic how often particular queries are run? No, it's based on the data. So in our triple store, we can find in just a microsecond or two how many, say, XY combinations we have for a particular predicate. And we also can do analysis of how many subjects we might expect for a particular, how many triples we might expect for a particular subject. And that is enough right now to do our queries, but there's a lot more that we can do to do more explicit statistics. But we'll keep working on that. And yeah, we've also been looking at doing parallel query execution, where you start multiple Prolog queries and then you look who's generating the most queries. But that's something that's also in research here.
Getting some good questions.
This is from Arthur Keen. Can you give insight into the factors that drive computational complexity in SPARQL queries? Well, yeah, SPARQL queries basically are, what you do is graph matching, and if you have a big branching factor in your graphs, then and if you don't do your reordering well, then you very quickly get into high complexity factors. Mostly it's branching factor in your data, and without an optimizer, if you say, if you don't do reordering for SPARQL and you would do a query where you say for every X that has Y and for every A that has B, and then after those two you finally start to mix the ABs and the XYs, then you already have created the product in the first two clauses of your SPARQL. And if you do that on a big database, you're instantly dead in the water. So all reorderness will always start with clause patterns where hopefully there's only one variable instead of two variables. Anyway, Arthur, there's so much more to be said about that. And then this is a question from Raymond. Is SPARQL the only RDF query language we're planning on supporting? I assume yes. No. I want to support both SPARQL and RDF. What I tried to explain in the beginning of my talk is, and something that became very clear when I was at in a life sciences conference in Boston last week, is where half of the people in the audience also knew Prolog. And the big difference between SPARQL and Prolog is that SPARQL is like SQL, it's an access language. But if you want to write complex applications, you not always can use only an access language. So things you see in SPARQL is you get really, really long queries sometimes because you can't do abstractions. Whereas in Prolog, you could take a really long query and take patterns that are part of this, make that into named functors or named rules or whatever you want to call it. And then your ultimate query will be shorter and much more readable because you can use abstractions.
Here's one back here.
Where can I locate tutorials or demonstrations? Oh yeah, so one of the things that we will do for people that want to try this out is we will, on our Java Learning Center, give you an example on how to run Lubum 50 and Lubum 8000 on the right kind of machine and how to do your queries. So you don't have to trust me. You can please do the queries yourself on your machine. I really have begged, do try this on the type of machine that I did it. So if you do this Lubum 8000, try it on a 16 gig machine because otherwise you will get not very good performance. Also, if you do it and you run it on EC2, where you can rent these machines, we've recently struggled with EC2. Months and months ago, EC2 was working great for us because when you got a machine instance, you got local disks. Now, when you run AllegroGraph on EC2, on the large instances, then you're not entirely sure where your disks are. It almost looks like your disks go over NSF. And when you get to the point where you have to page, then EC2 really, really gets slow. So query times in EC2 are a little bit slower than when you would do the same queries on a dedicated 16 gig machine. Yeah. And the question is, how do you deal with the inherent limitations of Prolog, such as order of rules? Yeah, that's a good question. So if you look at the Prolog queries that we optimize, then you'll see that most of the clauses in your Prolog queries are direct references to triples in the triple store or direct references to RDFS++ predicates. As long as you have those, then we can optimize Prolog. If you use a lot of rules or you embed many Lisp statements in your Prolog rules, then it gets a lot harder to optimize. I mean, if you use Prolog as a full programming language, then it's hard to optimize. If you use Prolog as partly an access language, then optimizing works a lot better.
Okay, well, I think we've addressed all the questions. You mentioned the Learning Center. Now, if someone wants to access immediately, again, we're a few days away. Some people wanted to say next week, but I urged to say a few days because it's less committal because it's software. We can provide you with a pre-release now, but the updates to the Learning Center that include what Jans mentioned won't be integrated until the final release gets shipped. And I will be sending out a special edition of the newsletter just announcing the 3.2 release once it's available on our website.
So what you see here is the Learning Center with AllegroGraph Java examples, with all the stuff that we do, from social network analysis, geospatial, temporal stuff. And here will be the benchmarks. For 3.2, you will not only see Lubum 50, but you also will see Lubum 8000 with instructions on how to build it on your own machine if you want to try it out.
Okay, one last look at the question log. How do we access this presentation contents later? I will be sending out an email message to everyone that registered and attended once this recording and the slides are posted on our website. They'll be located at the same page where you registered. It takes about 24 hours of post-processing just to get everything up and available. Okay, I think we're done, yes? And good presentation. We had a good topic today, and we're excited about it. We'll get this out as soon as we can, and we'll make sure it's good. So again, thank you everyone for attending.
Okay.
End the meeting now.
Bye-bye.